Okay, then good afternoon, everyone. Thank you for coming to this talk, which is in a series of IEICE Distinguished Lecturer Program online. Well, this program was previously held in person at various places worldwide, but because of the COVID-19, it was stopped for a while. And this year, we decided to hold it online. 2 weeks before, I think we had a talk of Professor Kenichi Sato on network architecture. It was the first one online. And today, this is the second. The title today is Physical Reservoir Computing, Its Advantages and Significance. Well, I think the reservoir computing will be more and more important framework in the information society. I will talk about this one. And the questions we are welcome at any time. Please use the chat, I think. I guess chat. I try to catch them, the questions. And also at the end of this talk, I will have a Q&A time. I'm Akira Hirose at the University of Tokyo, and we are the team of Professor Ryosho Nakane, the Graduate School of Engineering, and also Professor Gohei Tanaka, the International Research Center for Neuroinformatics, and I myself, all at the University of Tokyo. And the people of IBM Research Tokyo are also in cooperation. Dr. Jean-Benoît Hérault, Toshiyuki Yamane, Hidetoshi Numata, Daiju Nakano. We have been working together in a so-called socio cooperation program in the University of Tokyo. And now it is renewed and promoted as a NEDO project. So first of all, I would like to ask you, what is information processing? I wanted to ask someone by calling someone name, but I found there is no name on the screen in the attendance. So, okay, I think the answer is depending on situation and also person by person. And then that is why I wrote, what is your information processing here? Please imagine what is your information processing? What comes to your mind? Okay. Some people may say that high accuracy numerical calculation is the information processing. Yes, it is a very important point. And other people may think about the logical deductive inference. It is also very important. But in these years, people may answer to generate an appropriate response to the signals coming from outside. For example, automatic car driving, which makes an automobile really autonomous. It should sense a dangerous situation and decide to stop. This type of information processing increases its importance to a great extent in these years. Well, this type of information processing will be categorized into edge computing in the sensor network society. It should be real-time, ultra-low power, combined with sensors and so on. It takes place at the edge or at the end node of the sensor network. Well, the reservoir computing has its main application fields in this kind of engineering, but it is not limited. This is the outline of this talk today. First, we have a glance of neural hardware history, very briefly, and we visit fundamentals of neural networks. And then physical reservoir computing, in particular photonic reservoir modules and spin wave reservoir chips, and near future applications and a summary. And today's presentation uses much time for sections 1 and 2. This is because I would like to enhance the essence of neural networks, which is the basis of modern AI, and then the significance of physical reservoir computing. Otherwise, I'm afraid the physical reservoir computing will be under-evaluated very much. Please forgive me for this point. And I expect that many young students attend at this seminar. Then I also put stress on the basic conceptual parts of neural networks. I believe that they are meaningful also for those who are not so familiar with neural network theory. Well, neural hardware has a long history and many proposals in analog and digital areas. I pick up only a small part of the topics. This is an example. In 1980s, NEC Corporation sold a neural network board as an expansion board in its personal computers, Q801. Many senior people know this name, I think. Doctors Iwashita and Tenma employed data flow pipeline architecture by using image pipeline processors. And this is a very basic idea even now in present GPU and TPU systems. In 1990s, various analog neural devices were proposed. This is an example, floating gate transistor proposed by Professors Shibata and Omi. It works as a neuron, just like a neuron. It possesses multiple input gates and weights and some input signals, just like the neurons do. Silicon retina is another type. This is a resistive network investigated by Kawami and other many groups. It works like the network on our retina, retina. It's a little different from the central processing device, but its basic ideas are sometimes useful also for general neural networks widely. Similarly, Dr. Kumar, Ota-san, Funatsu-sensei group proposed the neural vision chip, Mitsubishi Electric people. It is now used in various image capturing systems and gaming machines. It spatially differentiates or integrates the image pixel values on the light receptive chip. This figure shows an example to extract edges of the input optical image. Memory star is a very attractive element. It was proposed by Professor Chua in 1970s, actually, originally as a missing element in electric circuit. But it is very attractive also for neural researchers later, since it is a memorable resistor and usable as a synaptic weight device. At the beginning, it was realized as an electric circuit shown here, but now it is fabricated as micro or nano devices based on, for example, phase transition phenomena. Spiking neurons are also very interesting. The use of spikes makes the multiplication at the synaptic weights very simple and easy. True North and Roy are the products of IBM and Intel, respectively. In the core process, they use the spiking neurons in its local operation, resulting in low power consumption. And for the remote communications among the cores, they use usual parallel paths for stable communications. And now we often use GPUs, graphics processing units. It is very digital, that is a bit machine. But the CPUs and memories are distributed in a fractional manner. TPU is the same. In these years, the bit number is getting smaller to realize fast and fast neural operation and lower power consumption. It suggests that such a simple bit machine may have inconsistency with the neurodynamics. Well, in this way, we go to digital and analog, swinging to gather good points in the respective architectures. And now we have the physical reservoir here in my context. Okay, this is another history shown in, say, in a chronological list, and it is concerning AI history. It picks up, again, only a part of the topics. At the bottom right-hand side, we see ENIAC and EDVAC. They are the first electronic computers. And we have a great development here in the logic AI. They works symbol or based way. Symbol based way means 1, 0 or bit or flag processing. And it is a great success, and we use computers every day. I hear that in 1950s, the people thought that artificial brain will be realized in this direction in a straightforward manner. But later, with the development of brain measurement techniques, we found that in our brain, the information is represented as patterns instead of 1, 0. The pattern is the spatio-temporal patterns of neuron firing. And it is very different from the symbols. The pattern information representation and the pattern information processing are the basis of neural networks. There have been many works in the neural networks area. And here we have neocognitron of Fukushima sensei and sound clock neural networks working as autoencoders. They are the basis of the present neural-based AIs, developed as the convolutional, in the wide sense, convolutional neural networks, deep learning, and so on. And we have reservoir computing here. Okay, neural networks. Well, I would like to discuss the very fundamental basis of brain and neural networks here. First of all, we compare the brain and the computers. This is the inside of a desktop computer. You use this kind of computers every day. We can see the motherboard in the depth, and behind the fan, there is a CPU, and we can see the memory slots here, and the hard disks, and video boards, and so on. They are the components inside. On the other hand, this is a set of MRI images of a head, human being's head. And this is actually my head. Several years ago, 10 years ago, I had a headache, and I was delighted. It's a good chance to obtain this kind of images of my brain. And I asked my doctor for the use of this MRI photos for this type of occasions. From the top left, cross-section of a little higher than eyeball level. Here, can you see? This is the cross section here. And lower, lower, lower at the level of the eyes. Sorry. From lower to higher, opposite. So higher, 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 and the higher part. The eyeball level cross section, nose and brain area. So here, a little higher. This. I was relieved to find something is inside. And a little higher. And we can see clearly the folds of the neocortex here. And the structure is a little different inside our brain from the computers. This view graph shows neurons. This is not my neuron, but I think it is a neuron in cat. The figures are copied from this book, Tsukada Sensei. And this cell is called pyramidal cell because it has a shape of pyramid. And it has many dendrites, these thin wires, dendrites. They are working as inputs. And in a slice of the brain, we often find a layer shown here on the right-hand side. The layer is consisting of cell somas distributed in a sheet way. And outside of this sheet, we can see only the dendrites here and here. And sometimes in other parts, we see a little more random distributions of the neuron cells. Well, the connections and the distributions are very complicated in the brain. And many people observe the firing pulses, electric pulses, traveling through the neurons and the axons and dendrites. But it was very, very complicated, not easy to understand what is happening in the brain. And in 1943, Macaro and Pitts proposed a model. What is a model? Well, a model is a simple idea extracted from the very complicated entity. Well, modelization is very important in understanding very complicated systems such as the society, our society, brains also. And this model of neuron, of a single neuron, is called Macaro-Pitts neuron model, or formal neuron model. And the most fundamental model, even now. And they extracted the following 2 points out of a neuron in the careful observations. The first one is that information is conveyed by the pulse rate in its average. That is, the pulse number in a unit time. And the second is the input rate and output rate relationship has a non-linearity, input, output, and non-linearity, including the threshold here and the saturation here. Then the output y is expressed by the nonlinear function. This is called an activation function, which activates a neuron. And summation of the weighted input signals and the threshold are very important. And this is the equation. This is the mark of a neuron. And this is the equation of Macrophage model. So the input signal here is weighted at the synapses and summed. And we may have a threshold and nonlinearity, and the output is generated. And this model is still the most basic model widely used. Then, well, on the left-hand side, this is the Macrophage neuron model. Then, if you are an electric engineer or students, you may think that, oh, okay, the neurons are very similar to gates. Gates that construct and logic or logic and so on in a conventional logic processing. It is true in some aspects. Well, here is an AND gate having 3 inputs. AND gate is represented or expressed in this way. What is 1? 1 is a step function shown here. If the input is positive, then its output is 1. If input is negative, then the output is 0. Step function. So we have, in this case, 3 inputs. And if we set the threshold at 2.5 as an example, then if the input, all the inputs are 1, the weights are always 1 unity. Then the total summation is 3, and this part is positive, and we get 1 as the output. Otherwise, the output is 0. This is the logic of AND. And if we set the threshold at 0.5, then if we have 1 input as 1 or more, then the output is 1. If all the input is 0, then only in this case, the output is 0. This is the OR operation. In such a way, by setting the threshold in an appropriate manner, we can realize AND or OR and whatever. Then they are very similar to each other. Then what is the difference between these two things? Well, the most important point is, I think, the number of the inputs. In the neuron case, we have hundreds of and thousands of inputs. Then the input in total is represented as the inner product of the input signals and the weights. Many, many. So inner product. Then this way of representation of information is called pattern information representation. That is, an information is represented by this signal, many, many input signals, thousands, instead of 1 or 2 or 3 or 10 at most. Then one single input changes, if any, is not so important because we have many inputs. And we get the input signals as inner product with the synaptic weights. And the output is obtained as the inner products again. So this processing is called pattern information processing. These 2 points are very important and related to each other. And they are very different from the von Neumann type computers. They are based on symbol information representation and processing, which uses the bits and flags. 1 bit is very important. So the efficiency is very high in the computers, but it is not so robust. Please consider that we are biological existence. So we lose our neurons every day, 1 or 10 or 100 neurons in our brain. But we don't have any difficulty, basically. In the morning, we get up, we don't feel anything difficult. This is because many inputs, so the representation and processing is based on the inner product. Then 1 bit or 1 neuron dead is not a great importance. But in the computers, if transistors die every day, 10 transistors every day, then the computers doesn't work. Very different. So this is one of the most important, we'll say, essence of the neural networks. Many neurons work, and the information is information serves as the inner product. So this is the pattern information representation and processing. In contrast, in von Neumann type computers, the symbol information representation, every bit holds a meaning. It's efficient, but not so robust in comparison with our brain. And it is also related to the generalization ability in our brain. Well, in this symbol case, we construct the computers in such a way that input 2, output 5, input, output. This is the truth table. And based on this table, we construct the combinatorial circuit. And finally, we can get the CPU. But this process or this direction has less generalization ability. 汎可能力. What is that? Well, this is a very important functionality of neural networks. Let's consider a supervised learning neural network. Well, some people are, I hope, very familiar with supervised learning. Well, it requires teachers, but anyway, the neural network learns the relationship between input and output. In this case, we show an input and output set as the teacher signals. For 2, the output should be 5. For 4 input, 6 is the output. For input 7, output should be 4. They are the teacher signals. And we apply certain algorithm to make the errors zero at these 3 points or teacher signal points. But in neural networks, what we really expect is this curve, not these 3 points. Well, it means that even if the neural network sees 3, for example, not 2, not 4, they are already shown to the network in the learning process. But 3 was not. Even in this case, 3 results in a certain appropriate output we expect. So we expect this curve, which corresponds to estimation or prediction. They are the set of non-used signals, not used in the learning process. This is very important. So then, with this generalization ability, we can be adaptive to the very varying environment. In contrast, if we are made in the lookup table way or bit machine way, then the generalization doesn't happen. So this way is named truth table in logic, and it works very well, but in a limited way. In the neural network, when it receives a new teacher signal, then the learn curve can be very different. This is also a very important point. In this way, the imagination ability, including estimation, prediction, and so on, is the very important. And this ability is called generalization. Then the next topic is the layers and deep learning. Okay, Macrophage neural model. X1, X2, they are the input signals. And we have W1, W2, they are the weights, which determine the transmittancy of the signals through the synapses. And this neuron generates output signals to transmit the signal through the axon. And, well, the one is many or high frequency pulses. 0 means no pulses. Medium is also possible. And the output is expressed in this way. So we have actually nonlinearity here, and also a threshold here, but we omit it here in this special case. I would like to explain another important point in the neural networks. That is the use of high dimensionality. Well, let's consider a classification of inputs. Well, we want to distinguish red apples from green peppers. How can we do that? Well, by applying a learning process, we adjust the weights here, and we get a suitable line showing the boundary between the peppers and the apples. This is the learning process in this case. And if the distributions of the signal is shown this way, then it works, and the program is named linearly separable program. It's okay. Then how about this one? A simple line cannot distinguish these ones from this one. In this case, we need 3 neurons. The first neuron do the same thing as the left-hand side neuron. Another neuron works in the same way, but makes a little different line here. And the third neuron do this one. And afterwards, the combining neuron extract this triangular area. In this way, even if the program is not linearly separable, this type of neural network can work. And this is very powerful. And in any case, it works very well with a certain initial states. In this sense, 2 layers are sufficient for any programs. 2 layers? Yes, the hidden layer, neuron layer, and the output neuron layer. Well, these inputs are also a layer, but they are not neurons. They are just terminals. Sometimes we call this one 3-layer neural networks, but in this sense, they should be 2 layers. But the problem is that our neocortex has 6 layers, actually. Why? This is the starting point of the deep learning, having many layers. In 1979, Fukushima sensei, Kunihiko Fukushima professor, Osaka University, but at that time, he was with the NHK, Nippon Hoso Kyokai. He proposed the neocognitron, a self-organizing neural network model for a mechanism of pattern recognition unaffected by shift in position. He paid attention to the local connections in the neocortex, which corresponds to the column structure perpendicular to the layers. This is column, representing these connections. And he prepared 6 layers. For what? Well, when we recognize the letter A, what occurs in the brain? He thought, we catch this sharp shape, and also these branches, and also these ends. And by combining these features, we construct A in the brain, and we recognize, this is the recognition of A. This is the idea. And this process is realized by the convolution and pooling. Then the scaling adaptability is realized, and also rotation robustness is also realized. Well, this is his proposal. the convolution layer, well, the name of the convolution, the word, is a little different from the mathematical convolution in image processing widely. This is the inner product, actually. This is not limited to neocognitron, but widely in the image processing. Convolution means inner product in most cases. But anyway, convolution and pooling to introduce the tolerance in the place or the rotation to some extent. Convolution layer, pooling layer, convolution pooling, and then this is the convolutional neural networks we often use in these years. This was a very great jump, which led to the present AI, neural-based AI. Another one is the autoencoder, or the sound clock type neural network. Well, even in those days, many people tried to increase the number of layers in neural networks. But in many cases, they didn't work very well, or they didn't show the improvement in its functionality. Why? The learning was not so well done. There are two problems. The first one is the vanishment of the gradient. For example, if we use a sigmoidal function, such as the so-called narrow meaning sigmoid or tangent hyperbolic, then the gradient of this nonlinearity shows almost zero derivatives here and here. And it means that the learning process has a very requires a very long time. And in these years, we often use the rectified linear unit. It is just like diode in electronics. So it solves this problem to some extent, because there is no nonlinearity here with the vanishing gradient. But here, in the negative part, the gradient is vanishing. So in this sense, it is not important idea, but anyway, many people use it now. Another point is the degeneration of signals going through neurons in a layer. Well, we have many layers, and we apply the learning process. And let's consider learning process here, these weights. By looking into this direction, into the output direction, because we often use the backpropagation learning, in which the teacher signals propagate backward to the input. Please assume that we look into this direction, at this cross-section. Then, if we prepare the weights at random, then the connections are very similar, very homogeneous, because the weights are initialized with a random function. Then the learning process cannot determine a clear direction into which the network should go. This is a type of degeneration, I think, and this is also a big problem. But by using the autoencoder process, this problem can be solved. Professor Gary Cottrell and his colleagues, and also some other groups, have been working on this topic. Well, what is autoencoder? Well, in usual, a neural network prepares a certain number of hidden neurons, or a big number of neurons here, so that the input signal is transformed into a higher dimension space. It is very important in neural networks. We'll go to this point later. But they thought, what happens when the hidden neurons number is very small? And they made experiments. What kind of experiments? This image is fed to the input of the neuron, and the same image is fed to the output of the neuron as a set of teacher signals. So this neural network generates the same information as the input. So it's a reconstruction. But because the number of the hidden neurons is very small, not all the information can go through this network. And what happens? Well, the output is very similar to the input. In this sense, the neural network works very successfully. And they found very important elements or features of inputs are observed in this hidden layer neurons. And this process is done automatically. It's a kind of encoder to reduce the noise, to reduce not so important information. So this is the autoencoder. And this is also widely used in processing even now, or more and more. But this process also means that the signals going through these hidden neurons are getting more independent to each other. It enhances the independence among the signals here. Well, this is a type of PCA, but well, the increase of the independence is the important point. Then we apply this autoencoder process in the multiple layer networks, in the initialization process. We apply it to determine the weights here, and then the signals are more independent to each other. And then we do the same thing in the next layer, and they are also independent, more independent than the random initialization. We do the same way, and afterwards, we apply the normal or backpropagation learning. Then the learning process works. This is the idea based on the autoencoder. So based on these ideas, so convolutional neural networks and the autoencoding process, we enjoy the deep learning process in these years. of course, there are other processes important, but these two are very, very important. Okay, we go back to this figure. Two-layer neurons are sufficient. But this process is also interpreted in the following way. Also, well, this distribution of the data is converted into a higher dimensional information process shown in the left-hand side. In this way. Then, by employing the higher dimension, this program is converted into a linearly separable process. It was not, but now it is linearly separable. In this sense, higher dimension is very important in neural networks. It is realized by preparing many neurons in the hidden layer. But at the same time, the nonlinearity is also important, because if we don't have any nonlinearity, then the transformation is results in this way. The nominal dimension may be increased, but the effective dimension is the same. Then it is not working. Okay. Well, this fact corresponds to the arithmetic of matrices. Two linear matrices multiplication results in a single matrix. Matrix by matrix results in a single matrix. By inserting a nonlinearity here, the matrix, both the matrices work in a meaningful way. So, if we have nonlinearity, then this situation happens. And also, if we have time domain, space domain, frequency domain, and so on in some way, then other natures are also usable. Hysteresis, anisotropy, dispersion, so on. There, the direct use of physical phenomena is suggested. Okay, we finally come to the reservoir computing. What is the time sequential or time serial information processing? Use of physical phenomena directly. So it should include delay, but at the same time, nonlinearity, or sometimes hysteresis and others. They can work as neurons. And they are useful in the time serial information processing. Input signal is represented in the time domain, and then this input generates many outputs in time series, and we choose use only the useful signals out of these generated signals to synthesize the desired output signal. This is the basic idea of reservoir computing. So this is a reservoir or a pond, and we throw a stone and we observe various waveforms, including nonlinearity, hysteresis, but they reflect the size of the stone, the weights, the velocity of the stone. And in this sense, the waveform is a transformed signal of the stone. Then we wait and gather the signals generated in this pond, and we synthesize the appropriate response. Okay, this is the reservoir. We may have multiple inputs, multiple outputs, and the reservoir part works just like the recurrent neural networks. In this case, we deal with time serial input signals. Then the neural network should include feedbacks or recurrence in its connection. And we apply the learning process only at the readout connections here to generate desired output. Well, if we have many neurons, enough number of neurons, then fast learning and low power consumption are realized. Also the processing, fast processing. And there have been many ideas proposed. One uses water, actually, with a bucket. They are mechanical hands to generate waves on the surface of the water. And we observe the wavefront with a camera. This is an overhead projector. I'm afraid young people don't know overhead projector, but I think senior persons know this one very well. Use this one in the presentations. Another idea is this one, soft material depth in the water, and the root of this octopus leg root is mechanically swung, and well, on the surface of this soft material, we put many sensors, and depending on the shape of this octopus leg, the sensor generates signals. These signals reflect the motion of the root, but very complicated. It works as a reservoir. But electrical engineers are interested in electronics or photonics. Photonic reservoirs are investigated for many years. Sometimes torque spin was used for electronics, and our group is also interested in spins, but spin waves. We visit these 2 areas. But anyway, reservoir can work as a signal processing module or system because of its nonlinearity and other nature found in material. By using material directly, we may realize very low energy consumption and very quick response computation with a high possibility. And sometimes it is very recommendable to use wave connections instead of wiring connections. And this approach is very different from the present GPU, TPU, and deep learning type of neural networks. Okay, we go to the optical ones and the electronic ones. Photonic reservoir computing. There are some types of photonic reservoir computing, but most of them use optical fibers, sometimes not. In this sense, they are one-dimensional. But sometimes we make an array of laser diodes or other optical devices to realize two-dimensional reservoir or planar circuits. This is a very typical structure of the photonic reservoir computing system. Here, photonic and electronic recurrence and also photodiode modulation nonlinearity are used. This is the laser diode optical source. And the light wave is modulated here with the input signal, and it propagates in the fiber to be detected at the photodiode. And the electrical signal goes back to the modulator. And the neuron signal is distributed in the time domain, or in this propagation in the spatial domain, but basically time domain. So we observe the output here to observe this waveform in the time domain. And the sampled points show respective neuron values, neural output values. And we weight these values and sum to obtain desired output. This feedback realizes complicated mixing or say interaction with the input signal, and this nonlinearity, the reservoir nonlinearity is realized. In the similar way, we may use an optical gain here, optical fiber amplifier, which realizes photonic nonlinearity, but other points are the same. Or we may use nonlinear electrical amplifier here. We convert the light wave into electrical wave, electrical signal by using photodiode here. And then nonlinearity in the amplifier, electrical amplifier, and VCSELs or other radar diodes to convert it into light wave. By using light wave, we can prepare a very long delay, time delay, so that we can put many neurons in this light optical fiber. Or laser diode itself can work as a reservoir in combination with external mirror. We look into this dynamics in detail. Well, this is the laser diode for oscillation. And here we have distributed black reflector mirror, DBR mirror here, which is modulated by the signal, input signals. And because of this external cavity, the laser oscillation is can be stable, unstable. But anyway, the output is detected at the photodiode, and we get AD converter, and we get the output here as the reservoir output. And this process, laser process, is represented by, say, rate equations or Lang-Kobayashi equations. So E1 is the electric field inside the laser diode, and N1 is the population inversion. N0 is the equivalent in the population, photonic constant, time constant. The external electric field, and so on. This is the electric field equation. And the electrons density are represented by this equation, including the injection current, injection to the laser diode here. Kappa is related to the reflectance of the external mirror. And then what happens? Well, we applied this system to a task to distinguish sinusoidal curves from triangular curves or time serial signals. And we observed the output light wave power here. This color map shows the laser oscillation complexity, which means that the number of temporal extremal values. So the white one shows very complex state, black not so. And the vertical axis shows the input current to the laser diode. And the horizontal axis shows the reflectance of the external mirror. Then we get this map. And if the input current is, the reflection from the output external mirror is very small, then the B state, output power is very stable. It's a normal laser diode oscillation. But if we have a higher reflectance, the oscillation is somewhat fluctuated. And here, the waveform is very complicated. Here it is almost chaotic, actually. And this curves shows the error rate of the distinction between the sinusoidal and triangular curves as a function of the input injection current. We also have the reflectance. And then it is very interesting that if the current is very small, then the oscillation is too stable that we cannot use the nonlinearity, and the error rate is very high. But it is very natural. But in the case of very complicated output signals, the white areas, it doesn't work again. Well, the injection current is very high. Then the signal is almost chaotic. Then it is not dependent on the input signals. It is independent of the signals, input signals. Then it cannot work as the distinguishing system. And it has very good areas, regions of the parameters here. And this area is called edge of chaos. So chaos itself is not important, not usable or useful, but the area near to the chaos is useful. Okay, this is an example of photonic reservoir dynamics. How about the spin waves? Spin waves are also very interesting and important, I think. We use garnet film here with the magnetoelectric coupling layer as an example, as the input and output layers, physical layer, with the conductive substrate on the back of the film. And, well, this is an example. Please consider 2 micron by 2 micron square chip of yttrium garnet film, which is a magnetic film. And we can analyze, or we design this kind of chips with a numerical simulation. We prepare a calculation mesh in space, in this case 10 nanometer by 10 nanometer, and in the time space also 0.01 nanosec to analyze what happens in this spin wave chip. These 2 circles show the input terminals, and we prepare many readout terminals on the chip, over the chip, as for the analysis, just analysis. This is not practical, but analysis. In this case, well, the task is very similar. Sinusoidal curve is distinguished from the square curve. This should be realized with a learning process with this chip. Well, this is an example we observe example of the waveforms observed in the chip. We have input terminals here at the top left and the bottom right. So we can see the wave propagates in the center direction. On the left-hand side, the sinusoidal wave is input for both of the 2 inputs. In contrast, the squared wave is fed to these 2 inputs. What do you think? Is it possible for the chip to distinguish one from another? They are very similar. They are very similar. It's true. But we can see differences here, with the precise observation. And the learning process applied to the readout weights extracts this difference in the time domain. In this particular case, the basic input frequency is about 2.5 gigahertz. The resulting waveform length is 2.2 micron over root 27 crests, resulting in 0.2 microns. And the wave phase speed is about 5.5 by 10 to the second meter by a sec. Through the learning process, we can map the obtained weights on the chip. Here, for example, the weight was positive, red one, positive here. Blue one, negative, positive, negative. White part shows almost zero weight. And it is very interesting that we can see the wave front is remaining, or the weight distribution reflects the wavefront shape. So the wave propagated in this way, correspondingly, this weight shows the same, very similar texture. And this is the output obtained after the learning process. In the red time area, the horizontal axis shows the time in the time steps, and one time step corresponds to 0.01 nanosecond. Well, here in the red area, the input signal is square. In the white area, the input signal is sinusoidal. And each strip corresponds to 1,000 little more time steps corresponding to 12.8 nanosecond, and again corresponding to 32 crests or waves, crests of this sinusoidal curve over the square curve. Well, we can see if square input is fed, then the output is almost 1. And the sinusoidal wave is fed, then output is almost 0. So the chip is successful in distinguishing between these two waveforms. Great. But we can also see errors here, or here, in the transient part. Well, because this is a time serial signal processing, then this type of error should occur in any case. It is unavoidable. But the transient area should be short as possible, as short as possible. And we check it. In this case, the transient is about 1 nanosecond, and it is almost 3 crests. 3 crests. That is, the chip observed the waves for this time duration corresponding to 3 crests. So then it is very short. Well, we can say that we should observe 1 crest at least to decide this is sinusoidal or this is square. This is the minimum, but the theoretical minimum. 3 is very small, very near to 1. So in this sense, it is a very good learning result. So in these cases, in photonic and spin wave reservoir computing, we showed today very simple tasks and the results. But these tasks can be more complicated, basically with a very simple manner. It is very easy. And they will be working effectively in the edge computing areas. There are a wide areas in the society: manufacturing, transportation, mobility, urban governance, public utility, medical areas, agriculture, energy, industrial safety, and so on. We can put many sensors with this processing units, and then we can reduce the transport or traffic in the networks, and we can reduce the burden in the cloud central computers with a very low energy consumption, because we use many sensors on this reservoir chip. then every set should be small in its power consumption. Okay, in this history, we have been based on ENIAC-EDVAC in its hardware, but now we opened the door to a new field, which is the physical reservoir computing, very different from the symbol processing. But this is based on the pattern information representation and the pattern information processing. This is very important in science and technology. Well, now the principle of the neural networks are the neural networks. AIs are neural networks. Previously, they were logic. Now, neural AI is the AI. But the hardware is still based on ENIAC. There is an inconsistency here. The functionality has an inconsistency with the hardware basis. So we need to construct a new hardware basis and the chips and the systems, which is based on physical reservoir devices. They should be the future neural AI devices, and they will work together in a complementary manner. So this idea will open completely a new world. So I would like to thank all the lab members, also Nakane Sensei, Tanaka Sensei, and also Natsaki Sensei. And please forgive me to have an advertisement on the neural network review paper in the journal Neural Networks in 2019, and also a book. This is a Japanese book, but Reservoir Computing 時系列パターン認識のための高速機械学習の理論ハードウェア、森北出版 published last year. And also, this is the last page. Another advertisement is on the IEEE WCGI 2024 to be held in Yokohama, Japan. So this is the web page, and probably many of you know WCGI. This is the largest and most important computational intelligence international conference consisting of IJCNN, IEEE CEC, and Fuzzy conferences, these three conferences, and will be held in Yokohama, Pacifico, Yokohama. I and Ishibuchi Sensei will serve as the organizing committee general chair. In neural networks, Christina will be the IJCNN conference chair, and the technical co-chairs are Zengwan, Barbara, Teresa, and Seiichi. And Fuzzy conference chairs are shown here, CEC, evolutionary computing here. And many people are involved, and I would like to ask more people to be involved. 大森先生、柴田先生、池田先生、我妻先生、吉本先生、and Donya Sensei, and Mitsukura Sensei, and Sato Sensei, many people. Okay. The time is over now. Sorry to have used all the time, but I'd like to receive questions. Thank you very much for your kind attention. Thank you. ありますね。 リザーバーの非線形性によって多様な信号が出力されると理解しましたが、ユーザーが求める信号を都合よく得るためには複数の信号をどのように組み合わせるのかが問題になる。そうですね。これは重みを決定と言い換えることもできるかもしれませんが、適切な重みを決定するプロセス自体は難しくないのですか。はい。おっしゃる通りの不安はあろうかと思います。I understand your anxiety, but it is very simple because the learning part is limited to a single layer. This is very important. It doesn't include any recurrent part of the reservoir computing. Okay. We apply the one or several, if needed, learning process only at this part. We don't apply any learning process here in the reservoir part in which includes recurrence. Of course, we have several ways, theory of recurrent neural network learning process, but they are often unstable or in many cases takes long time. Or in a special case, such as long short-term memory recurrent neural networks, they works okay, but they are a summation of the modules, prefabricated modules, prefab modules. So the application requires special architectures depending on the tasks. So it is not so good in this sense. But we apply only a single learning process on this readout layer. Then the learning process is very simple and very quick. Thank you for this question. Any other questions, please? Okay, so the time is over. I'm sorry that I used much time, but please feel free to make emails. ありがとうございます。To make emails to me or yes, I will do my best to answer your questions at any time. And please come to Yokohama 2 years later to discuss anything on reservoir computing and other neural networks, other information processing and devices. Okay, that's all today. Thank you for your kind attention. Thank you very much.